So, before the break we were talking about the Brownian motion and the stock price models. Before I conclude that topic, I would like to emphasize once again that the infinitesimal model has a mean of mu s is normally involves the normal distribution of the, let us call it the change in stock price ds. ds is normally distributed as mu s t t and a variance of sigma s d t, sigma square s square d t, mean of mu s t t and variance of sigma square s square d t. Whereas, in the finite model, finite time model, log s is normally distributed with a mean of log of s naught plus mu minus 1 by 2 sigma square t and a variance of sigma square t. Now, the important issue here that I would like to highlight is that in this model, in the log normal model, the mean and the variance are independent of the stock price, whereas in the infinitesimal model the mean and the variance both are functions of the instantaneous stock price. So, this has to be taken care of, and in fact, this is one of the reasons or perhaps the primary reason why this infinitesimal model cannot be extended for longer time periods. Right. Now, coming back to the new topic that I had in the agenda for today, we now move to the option pricing models. We have talked about stochastic calculus, we have talked about modeling of stock prices. Our next step is to model derivatives based on stock prices, that is, we are going to model option prices based on these stock price models that we have been talking about so far. Now, there are two fundamental models, two basic models. Of course, there is a wide variety of variations of them, but there are two fundamental models. One is a discrete time, discrete variable model, which is called the binomial model, and the other is the continuous time, continuous variable variant of this model, which is called the Black-Scholes model. We will initially start with, although the underlying philosophy of both the models is precisely the same, we shall start with the binomial model and then move on to the Black-Scholes model. So, let us start with the binomial model. You see, when we talk about pricing of derivatives, we are essentially again one of the approaches rather is again to invoke the principle of arbitrage. What we say is that because the source of randomness in the stock, that is the underlying asset, and the derivative which depends on the underlying asset is the same. Therefore, we should at least in theory be able to construct a portfolio consisting of a combination of the derivative and the underlying asset, such that the fluctuations of one or the randomness in one is annulled by the randomness of the other, and we end up with an asset which has no randomness. That is the underlying philosophy of both the binomial model and the Black-Scholes model. The only difference is perhaps that the binomial model operates in a discrete framework and is thereby relatively easier to comprehend, whereas the Black-Scholes model is slightly more extensive. It uses a comprehensive continuous time calculus to arrive at a similar scenario. We shall start with the binomial model. So, to reiterate, because the randomness embedded in both the stock price and the derivative originates from the same source or is modeled by the same Brownian motion or the same random walk, we accept or we assume that somehow or the other we can construct a portfolio which comprises of positions in the two assets, the derivative and the underlying, such that the randomness is annulled. So, we can write this as what I have mentioned just now can be put quantitatively as derivative is equal to delta, delta is the number into underlying assets, certain number of units of the underlying asset. It may, you see, one derivative may not relate to one unit of the underlying asset, there may be a difference between them. What the difference comes out to, we will come back to it. So, derivative is equal or derivative minus delta into underlying asset, because the randomness cancels, we are left with the risk free asset. So, derivative minus delta into underlying asset is the risk free asset, or you can also view it as a derivative is a combination of a certain position in the underlying asset plus a certain position in risk free bonds. And in fact, it also amounts to saying that a derivative can be constructed synthetically by taking appropriate positions in the underlying asset and risk free bonds. Let us start with the simplest model, the single period binomial pricing model. You would recall that we started the discussion on stochastic processes by a single step random walk, where a particular walker had the discretion either to move up or to move down, but he had no inkling of which is more appropriate. So, what he simply did was he tossed a coin, and on the basis of the result of the toss he either moved up or he moved down. In other words, he selected the direction of motion randomly, absolutely randomly. This is more or less a similar scenario. We have a single step random walk. The stock is initially at point S0, is priced at S0, it is priced at S0 and at t equal to 0, and from S0 at a certain point, remember we are using discrete time. So, time will move in steps, in discontinuous steps. We cannot have, we are not talking about continuous time. So, at t equal to 0, the stock price is 0. Now, the next move will come at a certain point in time, let us say that is it at t equal to small t. At that point, the stock price either moves up to SU or it moves down to ST. It can take only these two values, SU and ST. The interval between 0 and this first jump is t, which is the time length, and in between, in this time length, the stock price cannot perform any movement, cannot move up or down, it remains stationary. Only when the clock ticks t, it makes a jump. It makes a jump randomly either upwards to SU or downwards to SD. It is a single step model. So, that is all we are going to talk about. We write SU in terms of the percentage change with respect to S0 as S0u, and similarly we write ST as S0d, where d is the percentage change. This is important, there will be no change in the stock value in the interval 0 t, because it is a single period model. At the end of this interval, the stock price will either jump up or it will jump down. Now, what do? We construct a portfolio consisting of, as I mentioned just now, we construct a portfolio consisting of one unit of the derivative, let it cost f0. Let the cost of the derivative be f0 at t equal to 0. We are constructing this portfolio at t equal to 0. This portfolio is named V. It consists of one unit of the derivative and delta units of the stock. So, 1 unit of the derivative costing f0 at t equal to 0 and delta units of the stock, 1 unit of the stock costing S0. So, delta units costing delta S0. So, the total value of this portfolio at t equal to 0 is given by f0 plus delta S0. This is the value of the portfolio at t equal to 0, let us call it V0. Now, what happens at t equal to small t? At t equal to t, the stock jumps either upwards or downwards, it jumps to S0u or it jumps to S0d. At the same time, the derivative may make a payoff. Let us assume that the derivative makes a payoff of fu if the stock price goes up and it makes a payoff FD if the stock price goes down. Then what will be the value of the portfolio if the stock price goes up? It will be equal to FU, because this is going to be the value of the derivative. This is what the derivative is going to give me, and delta, because there are delta units of the stock, into SU, because now the price of the stock is SU, and that is S0U or SU. So, this is the value of the portfolio if the stock price goes up, and similarly if the stock price goes down, the value of this portfolio becomes FTD, because this is the derivative's payoff. Remember, it may be 0, it is not necessarily that the derivative payoff must be positive or even negative, could well be 0 also. So, VD is equal to FDT, that is the payoff from the derivative if the stock price goes down, and if the stock price goes down, its price per unit goes to ST, and because we have delta units of the stock, the total value of the portfolio becomes FTD plus delta ST. Now, if the portfolio is to be riskless, that is our argument that we can construct a portfolio consisting of the derivative and the underlying asset which is riskless, which is risk free, which contains no fluctuation. Now, if the portfolio is to be riskless, then its value must be independent of the stock price at t equal to t. In other words, whether the stock price goes up or the stock price goes down, the value of the portfolio should remain unchanged. Therefore, we must have this expression must be equal to this expression, and on simplifying this we get delta is equal to minus of this divided by this. Change difference between the derivative payoffs divided by difference between the stock prices. Now, what is this minus sign? This minus sign represents that the position of the stock must be opposite to the position of the derivative. In other words, if you are long in the derivative, you should take a short position in the stock and vice versa. So, let us do some calculations now. Now, because this portfolio is risk free, we have assumed that this portfolio is risk free, we have annulled the risk, and because it is risk free, it will generate risk free return over 0 t, and therefore, if it is worth V 0 at t equal to 0, it must be worth V 0 e to the power r t, assuming continuous compounding, V 0 e to the power r t at t equal to t. Therefore, we must have V t is equal to V 0 e to the power r t, and this expression we have already agreed. This expression represents that the portfolio is independent of the direction of movement of the stock price. Therefore, equating the two values of V t, this is one value of V t, this is the other value of V t, we have this expression is equal to this expression. Substituting the value of delta that we worked out earlier, that we worked out from these two, in fact, we get f 0 is equal to, now this is from the first equation, f 0 is equal to V 0 minus delta S 0. So, V 0 is equal to V t e to the power minus r t, discounting it backwards, minus delta S 0, delta is given and S 0 is also known to us. So, we are simply plugging in the values. V t, you can take either this one or you can take the f d one, it does not make any difference, you end up with the same values subsequently, does not make any difference. So, let us take it as f u plus delta S u e to the power, this is V t e to the power minus r t is V 0, V 0 minus delta S 0 is f 0. This is what this equation represents. We plug in the values of delta, we get this expression e to the power minus r t into this whole expression. And if we take e to the power minus r t common, we get this expression. This gets multiplied by e to the power r t, because we are taking e to the power minus r t outside the brackets. This is what we had in the previous slide. Now, slight rearrangement can give us this. No change, simply a rearrangement of the quantities has been done, and we get this expression f t into this plus f u into this. Let us write this as QU, or sorry, QD, and let us write this as QU. Then we can write it as this whole expression e to the power minus RT QUFT, QDFT plus QUFU, and that is nothing but e to the power minus RT EQ. From where I have got EQ, I am just going to explain, but for the moment it is expectation with respect to Q. We will come back to it. Why we can write it like this, we are coming back to it in the next slide. For the moment we are simply writing it like this, and we are interpreting this as QU as QD, and we are expressing this as QD, QU. This is QD, this is QU. Let us move on. This is QD, this expression is QD, QD gets multiplied by FT and QU gets multiplied by FU. So, we have FT QD plus FU QU. Now, if you look at this carefully, this is very obvious. The S0 e to the power RT and this gets cancelled, we get SU minus ST, that gives us 1. So, what do we have? We have QU plus QD, QU plus QD is equal to 1. That is the first expression. The second contention is that both these expressions, this expression and this expression, both lie between 0 and 1. That is my argument. Why it is so? Let us see. Let us start with this one. This I think is QU. Yes, it is QU. So, S0 e to the power RT minus ST, SU minus ST is greater than 1. Let us see why. Now, what does it mean? If this is greater than 1, then what happens? Then we have S0 e to the power RT is greater than SU ST. You see, when you cross multiply by SU minus ST, because that is positive, so there is no problem regarding sign. You can cross multiply both sides, you can multiply both sides by SU minus ST, because this is positive, and this inequality will remain unchanged. ST and SD will cancel out. You get S0 e to the power RT is greater than SU. Try to understand what does this signify. What is SU? Now, SU is the maximum value that the stock can take at t equal to capital T. In other words, this is the maximum return, or this is equivalent to, or this represents the stock price corresponding to the maximum return that can be generated on this stock. And remember, the stock is risky. The stock is risky. The stock is risky, and SU corresponds to the maximum return on the stock. So, if you are saying that S0 e to the power RT is greater than SU, you are simply saying that the risk free return which is embedded in this, is higher than the highest possible return, the best possible scenario on the stock. Can this happen? The stock is risky and it gives you a lower return than the risk free asset. Would anybody, any rational individual, any rational investor invest in this stock? Everybody would go for the risk free asset, because the risk free asset is not only giving you a high return, it is also giving you a high return with certainty. And because it is giving you a high return with certainty, it is certainly superior to a stock which is giving you a relatively lower return at the best case scenario. So, this cannot sustain in the market. The risk free asset will increase in demand, the demand for the risk free asset will escalate, the demand for the stock will completely diminish, and the returns will start realigning themselves, so that this inequality is not satisfied, and we must have, this must be less than 1. And similarly, we can prove the other inequalities that are there, that QU must be greater than 0, and similar bounds must exist for QD as well. The bottom line is that both QU and QD satisfy two fundamental axioms. Their sum is equal to 1 and they lie between 0 and 1. That being the case, we can interpret in some sense this QU and QD as some sort of probabilities. Remember, they are not real life probabilities. They are not probabilities that have been found by experiment and observation. They are simply mathematical constructs. They are mathematical constructs, but they are mathematical constructs that seem to satisfy the axioms of probability. So, we call them probabilities, but we also call them synthetic probabilities. The important thing is these are synthetic probabilities. We will learn more about their nature immediately. Let us work out. So, since now that we are agreeing to call a QU and QD as probabilities, albeit synthetic probabilities, but probabilities nonetheless, we can also define an expectation. We can define an expectation in terms of these probabilities. Let us call it EQ, E with the subset Q, E subject to the probability measure Q. Let us work out the expectation of the stock price. Remember, earlier we were talking about the derivative price. Now, we are talking about the stock price. Let us work out the expectation of the stock price at a certain future time period t using these synthetic probabilities. What do we get? We get, there are two possibilities for the stock price. Stock price can go to ST or the stock price can go to SU, and the probabilities is QU and QD. So, what will we have? QU SU plus QD ST. Simply putting the values of QD and QU, we find that EQ ST is equal to S0 e to the power RT. EQST is equal to S0 e to the power RT. What does it mean? It means that these synthetic probabilities are such that the expectation that we get for the stock price, at a future date implies a risk free return. The expectation worked out with respect to these synthetic probabilities is has such a value that it gives us a risk free return. How can this happen? What is the implication of this? There are two important issues in this context. Number one, remember, stock price is a risky asset. It is not a risk free asset, it is not a bond, it is a risky asset. So, the first contention the first inference that we draw is that all investors, irrespective of the risk profile of the investment, are accepting the same return. Why is that? Well, it is only then that this R is assumed to be constant for all the investors. If R is assumed to be constant for all the investors, that means all the investors are accepting the same return. And if all the investors are accepting the same return, it means, it can mean only one thing, that they are indifferent to risk. Stock price is a risky asset and still you are accepting a risk free return. That clearly means that you are not concerned about the risk, you are not bothered about the risk, you are not considering risk as a valuable input into your investment decision. In other words, putting it more precisely, you are risk neutral, you are not influenced by risk, your decision is based purely on return. Then we come to the next question. The next question is, why risk free return? The first thing is that all of the investors are accepting the same return, that is the first issue, and that implies that the investors are not concerned with the risk of the asset. And the second thing is that all investors are accepting which return? The risk free return. Why it has to be the risk free return? Let us say we have two assets. Let us say we have two assets, asset A or asset X and asset Y. Let us say asset X gives you a higher return than asset Y. Asset X gives you a higher return than asset Y, but asset A is extremely risky compared to asset Y, and that is why it is giving a higher return. That is logical, expected return of course. If asset X is giving you a higher return than asset Y, and asset X is having a higher risk, but all the investor fraternity are not bothered about risk, then everybody would go and invest for asset X. Why? Because then return constitutes the only criterion for investment. Risk is gone out of the window. So, return constitutes the only criterion for investment, and because asset X is giving you a higher return than asset Y, albeit at a higher risk, that higher risk is irrelevant, and because the return is higher, everybody flocks to asset X. So, what does happen? The demand for asset X picks up gigantically, and asset Y drops to doldrums. If that happens, what happens to the respective prices? The prices also realign themselves, and as a result of which both the assets will generate the same return. And why is that? Because both the assets will generate the same return. Why? Because risk is irrelevant. Asset X's risk is not a decision making content, contains no decision making content, and therefore, it is irrelevant. So, that being the case, the return of asset X will be pulled down to the return of Y, and therefore, at the threshold level, all investors will receive the risk free return, because any asset having any risk will tend to provide a higher return than the risk free return, and as soon as it provides a higher return than the risk free return, that differential will be eaten away by arbitrage, and it will go down to the risk free level, and all the investors will therefore receive only the risk free level. No asset can give you, no asset whether risky or not can give you return higher than the risk free asset, and by nature, because the risk free asset has zero risk, it is supposed to provide the lowest return, right. So, that being the case, we interpret these synthetic probabilities, because synthetic probabilities now brought to us the concept of risk neutrality, and therefore, we call the synthetic probabilities as risk neutral probabilities. They are given a specific name. These Q probabilities, these synthetic probabilities are given a name. They are called risk neutral probabilities. But the important thing again I say is that they are not real life probabilities. They do not emerge out of actual experimentation and observation and inferences. They are simply mathematical constructs. Hence, we conclude that the price of the derivative is the present value. Let me write it down. The price of a derivative, let us call it C. Price of the derivative is the present value of the expectation of the payoff from the derivative on the date of maturity, that expectation being calculated with respect to risk neutral probabilities. Now, there is a very important question, that why is it that real world probabilities are thrown out of the window, do not contribute to the pricing of the derivative. It is a very interesting question. Let me explain it. How did we do the pricing? We did the pricing by taking a position in the derivative, taking a counter position in the underlying asset, and making the assumption that the randomness in the derivative kills the randomness in the underlying asset or vice versa. And as a result of this two, the portfolio that we have is risk free, and then we valued that risk free portfolio. Now, because we have not valued the derivative in isolation, we have valued a portfolio consisting of the derivative and the stock as a risk free asset. We said that this is a risk free asset, so it is going to generate risk free return, and then we said that okay, because it is generating risk free return, okay, risk free, the derivative plus the stock is plus minus the stock is equal to the risk free return in a sense, in a crude sense, and therefore derivative is equal to the risk free return minus the stock. Now, the stock price, the important thing here is, as far as the risk free asset is concerned, it is giving the risk free return, so there is no issue with that. As far as the real world probabilities, the issue of real world probabilities is concerned, the stock price encodes everything in its price about the real world probabilities. The price that prevails as on a particular date covers everything about the perceived future behavior, what the market perceives about the future behavior of the stock, and therefore, that stock price encodes the real world probabilities. Therefore, because we are valuing the derivative not directly as the derivative itself, but as a no arbitrage combination of the risk free asset and the stock contains the information on the real world probabilities, we do not need to consider real world probabilities in the context of the derivative. Right, we will continue from here in the next class. Thank you.